right? And what that is that's basically just this pendulum which you just shoot a bullet into, right? It's used to measure what the speed might be of your projectile, right? Because you can conserve energy and do this analysis, which is exactly what we're going to do right now, right? So you have a 6-gram bullet, which is bullet, they say it's the bullet A, right? So that's the bullet A is fired into this block B, which has a mass of 1 kilograms, and the length of this cord is 2.2 meters, right? So you're asked, the block then swings up through a maximum angle of 60 degrees. It swings up 60 degrees, and then it's stationary at this point. So what you're asked to find is, you're asked to find the initial speed of the bullet V naught, right? And then you're asked to find the impulse that's imparted by the bullet onto the block, right? And you're asked to find the force on this cord right after this bullet dislodges into this mast over here, right? So when I'm looking at this problem, obviously, before impact, this V naught is unknown. And then after impact, the velocity of this combined body is unknown, right? So before impact, V naught, come on, V naught, so bad, is unknown. Come on, dude, is unknown. I don't know what's happening to my screen, guys. All right, so before impact, V naught is unknown. And then right after impact, right, let's call it V1 of the combined mass of A and B with the bullet dislodged in. We're not assuming that any mass gets lost, right? So the combined V1 of A and B is unknown. Right? V1, we can straight away, so basically 2 unknowns. What that means is you need 2 expressions. V1, we can find easily, right? Because we can do a conservation of energy for saying that, all right, there's this combined mass which has a velocity V1 at this position B, and when it moves into this position, let's say this position is, let's call it position C or whatever, it stops, so I can conserve the energy and figure out. So if I draw my datum out over there, I can conserve energy right after impact from B to C to figure out what V1 is going to be, right? And before impact, I can relate that to V naught using the principle of impulse and momentum to figure it out. So that way I get my 2 expressions for 2 unknowns. So this one, right, is going to be with impulse, momentum. And this one's going to be solved with energy conservation. All right, I keep saying energy conservation. I should stop saying that. Work energy principle. Right, so instead of saying A, B, C like this, right, that's terrible. Let's say that this is position 1, and let's say that is position 2. And I've defined my datum down, right? I know that this length is L downwards, and that this length from my datum for my potential energy is going to equal what, guys?
L minus L cos theta.
Well, that's if you use your datum from here. If you're saying that the datum is from the top, then it's just going to equal L cosine theta, right? Is that right? Yeah, that's right.
Yes.
Okay. All right, so now let's do the energy conservation, right? So that's the easy stuff. So apply work energy principle. Right, so we can say that the kinetic energy at position 1 plus the potential energy due to gravity at position 1 There's no non-conservative forces, right? So I don't need to worry about anything. It's going to equal my kinetic energy at position 2 plus the potential energy at position 2, right? So, and in this expression, straight away, what's this kinetic energy at position 2? At this position here? Zero, right? Because it comes to a rest there. That's the whole concept of this thing. So this guy is equal to 0, right? So we can write T1, and remember, T1 is for the combined mass of its after impact, right? So this expression T1 is just going to equal 1/2 times the mass of your combined block and bullet. So it'll be MA plus MB times V1 squared, like that, right? And because we said that the datum is on top and we're measuring downward from it, remember your sign convention, going downwards, right? The positive X and Y axis and things like that. This will be minus times MA plus MB times GL. All right, and that's going to equal minus MA plus MB times G times L cosine theta. And remember, the negative sign is because the datum, you're measuring downward from it, right? And remember, positive Y and X axis. We always keep that consistent. The other way to look at it would be to take your datum at B, and then you just get L minus L cosine theta, which is positive, which, whichever
Why
way
is
you
it
guys.
L cosine theta and not L sine theta?
Because this is L, and this component here is going to be L cosine theta, and that is going to be L sine theta. Is that clear?
I'm processing it, yeah.
So whenever you have something like that, right? Opposite, this is theta. This side here, the adjacent side, this is L cosine theta, and the opposite side is L sine theta, right? So here, this is the adjacent side, so that's L cosine theta.
Oh, right.
All
Yeah,
right.
I'm so used to the y-axis being sine and the x-axis being cosine.
No. It's in reference to where your theta is. I could give it to you in any direction, right? So if this is L, and I ask you to find what's this component going to equal, that's always going to equal L cosine theta, and this component here is going to be L sine theta.
I see. Awesome.
All right, so all of the masses go away, right? And you end up with the expression for V1 is equal to the square root of 2 GL times 1 minus cosine theta, like that. All right, and everything inside is known. So I guess we should have written that out. But anyways, you guys, square root of 2 times 9.81 times L, which is 2.2 meters. Make sure all the units are correct. Here it's meters, times 1 minus theta, which cosine theta, which is 60 degrees. So 1 minus cosine 60 degrees, right? So this ends up being equal to, I have 4.646 meters per second. All right, so this is my second expression where I found out V1, but I don't need to know V1. I need to know what V0 is. And for that, I've got to use my impulse momentum issue, right? So with the impulse momentum issue, what you're doing is for V0, right? So if you look at your diagram, you can do this straight away if you guys are comfortable with it, but just for explanation's sake for you guys, right before impact, you have the block and you have the bullet, right? And here and you'll remember you're looking at the momentum of the system together, right? So this is for the system. Here, only the bullet is moving, so the only momentum before impact that you have is going to equal ma times v0, right? Then you're going to have the requisite impulse which happens, which is just going to be 0, right? So you can just say that the impulse is 0 because there's no actual physical force. But if you want to look at it the hard and fast way, right? At that, it's just going to be an equal and opposite impulse which gets lost for the whole system. So you'll have F dt for that guy, and you have an F dt for that guy, right? If this is confusing, much more makes sense that this is just equal to 0. That's okay. It's just equal to 0. Right? But the equal and opposite reaction due to the impact is why this impulse is equal to 0. You're not physically putting any force into the system. That's how you can think of it. All right. But for some of you, this might make sense. So there you go. You get both ways to do it. All right. And that is equal to the final momentum of the system when the bullet gets dislodged in and they start moving together together, right? So this is going to be, and remember, this is all an direct impact, right? So along the line of impact. So this is going to be MA plus MB times V1, like that, right? And this gives you your second expression, which you need to relate V1 to V0, right? So you get MA times V0 is equal to MA plus MB times V1, right? Or V0 is equal to MA plus MB divided by MA times V1. So this just turns out to be equal to the masses are 6 grams and 1 kilogram. Wow, that's a lot. So mass A is 0.006 kilograms. Is that right? 6 grams, yep. Plus 1 divided by 0.006. Such an idiot I am. 0.006. There you go. Yeah, like that. That times V1, which is 4.646. Again, make sure your units are all good, right? So this is kilogram, 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 all right? And then you have meters per second here. So you'll end up with meters per second. So this tells you that your initial speed, V0, we already know the direction, it's horizontal. So V0 ends up being equal to 778.92. And there you go. You set this up, right? So you're physically solving this problem, but suppose you're working at the gun range and you're like, all right, I have the system to figure out what the velocity of something is before it hits my block, right? You can just spread up, you can just set up your Mathematica spreadsheet in terms of all of these unknowns and just figure, all right, the angle comes out to be equal to this, plug that in. The length of the cord is this, plug that in. And you will automatically get what your initial velocity is, right? So that's what this problem-solving aspect of things might apply to in a real condition, right? Or if you guys decide that you want to start a company where you're manufacturing these things that you sell to gun ranges, then you can make a software for it, which basically does all this analysis for you, right? You already have all you are just this formula, which you can pretty much put into like a spreadsheet and figure it out. All right, so you find out what your initial velocity is. Next, your question is asking you to find out what the impulse imparted onto the block is. So now you need to look at the impulse momentum for just the block. And that's why, all right, I said that you might not need to look at this, but you kind of do, because this is what's happening just to the block now, right? So if you're looking at just the block, anyways, before I move on, any questions up to this point? All right, and everyone is down, right? I can move on to the next page. Good? Good? No, good? Good? Good?
Yeah,
All right.
well, good.
All right, so for part B of the problem, you're looking at just the block now, right? So for just the block, before the impact, it's moving at 0 velocity, right? And the only thing that happens is it gets impacted, right? It gets impacted by the bullet, like that. And that ends up in the motion of this block, right? So it's MB times 0 here, and this one is MB times V1, like that, right? So if you write the expression out, all right, to be complete, right, you would say that you have your momentum here, which is just 0, because it's stationary before the impact of the bullet, right? Now, if you write this expression out, you'll see that your impulse force plus 0 is equal to MB times V1. Now you're just looking at the block itself. So you have to take the bullet out of it. And therefore that just gives you what your impact force is, right? So that's just, so your impulse is just equal to MB, which is 1 kilogram times V1, which was 4.646, right? And this comes out to be equal to GH 6 kilograms meters per second. Good. Okay, so this is your impulse force. So that's the answer, pretty much. Your impact. The impulse, sorry, the impulse that's imparted by the bullet onto the block. Yeah.
It wouldn't be the mass of A plus B?
No, because now you're looking just at the block. If you're looking at the combined system, there is no impulse, right? Because of the equal and opposite reactions. So you're looking at just at the block.
Makes sense.
Finally, you're asked to find the force. Again, guys, it looks like we'll be going over time, which is just due for the course for us at this point. I'm sorry, we'll be going 5 minutes over because we have to look at another problem. So if you look at part C, right, you're asked to find the force on the cord immediately after impact, right? And here you have to use Newton's second law, right? So right after impact, if I draw my free body diagram out, so this is going to be Newton's second law, right? I'll have my free body diagram for the bullet that's imparted onto the thing, right? I'll have the weight, which is MA plus MB times G. Then I'll have the tension in the cord right after impact, right? And here, it's best to look at normal and tangential components, right? Because you have a circular path, and you'll see in a minute why. So this is equal to my kinetic diagram, which is just, you can say that is MA plus MB times the normal direction, and I'll have MA plus MB in the tangential direction, right? But I don't need to worry about the tangential direction. This is just going to equal 0 because there's no forces in the tangential direction, right? But anyways, don't worry about it. If that doesn't make sense, you don't need to worry about it because we're not looking at that at all. All you need to do is look at Newton's second law in your normal direction, right? And that's going to equal MAN like that, right? So you get T minus MA plus MB, knowing that the positive direction is upward. G is equal to MA plus MB times your normal acceleration. But how do I find out what my normal acceleration is? And I'm looking at the normal and my tangential components. Radius of curvature. What? Someone said something?
Would that be V squared over L?
Absolutely. So 1 V1 squared over L, right? Because here you're going to have a circular path. Whoops. You're going to have a circular path whereby L is your radius of curvature, right? So that normal acceleration is always going to hold true like that. It's going to be v1 squared over L like that, right? And then you can solve for this to find out that your tension force is equal to MA plus MB times v1 squared over L plus G. And everything in here is known. I'll give you guys what the final answer is. It is 19.74 newtons. Good. Okay, we are going to go 5 minutes over, so bear with me, all right? Or maybe not. We can do this relatively quickly. All right. But before we move on to the next problem, do you guys have any questions with this one?
Nope.
All right. Next question is pretty straightforward problem in terms of what's going on. It's just directly what we're applying, but it's, you just have to figure the small things out. You have hockey pucks, which are identical, and they're moving in a hockey rink at the same speed of VA and VB equals to 3 meters per second, but the directions in which they're moving are clearly different. All right. And you're told that they strike each other as shown, and you're told that there is a coefficient of restitution, right? So you do have some energy that's lost to your surroundings. And you're asked to find the direction and the magnitude of the velocity after the impact takes place. All right. So straight away, this is an oblique impact problem. Right? So let's set up our relationships that we had set up when we were looking at the theory, right? We don't need to worry about impulse and at all, because that only comes into the picture when you're looking at the individual balls, but not for the system, right? We don't need to worry about it. So let's see. That, right? You've got your tangential direction, you've got your line of impact, like that, right? And you know that, whoop, shouldn't draw that, Control Z. Oh no, oh no. Come on.
RIP.
This happened to me on Tuesday as well, and I had to cancel my class because all my lecture notes were in there and I hadn't saved the file. And I think I've done the same thing again. All right, fun times. What needs to get
PowerPoint
saved?
doesn't want you going overtime, I guess.
Is that no responding again?
Yep, same thing, and it's crashed. There you go. Bye bye.
Yeah, I had the same problem this morning, and I lost my essay.
Oh no. Yeah. Well, let's see what it's recovered. Yeah, not bad. All right. Well, we missed all of the part over here, but who cares? You guys have the solution. All right. So, all right. So here we go to remember that it is oblique impact, right? So when you're looking at the oblique impact, ball number 1, ball number 2, and despite what this drawing tells you, these guys are the same, like that over there, right? So here we're told, if I draw the horizontal out, that this angle is 20 degrees, right? So what that means is that this angle here is also going to be equal to 20 degrees, right? And if I draw a straight line down from here, right, this angle here is also going to equal 20 degrees. All right, so that's the important thing. Then we're told, if I look at the centers of these guys, I have my initial MVA like that, and then perpendicular to it, I have MVB like that, right? And this is before impact. Now remember, we're using normal and tangential directions here. So define those when you're writing it out, right? So you have normal direction, which is positive in that way, the tangential direction, which is positive upwards, right? That becomes necessary when you're assuming unknowns, right? Because it's always better to assume unknowns in the positive direction. So after impact, when you're looking at the balls, right? So you've got tangential and normal like that. Remember, we'll have 4 unknowns. So if I write those out, I'll have this like that. So it's going to be m, and the mass is the same. That's why the m is like that. So m times VA prime, the normal direction, and then make a positive one as well. So m times VA in the tangential direction. Almost did a control Z again. Like that. And then for this one, again, unknowns, make it positive unknown. So you have m times VB prime, normal like that. You have m times VA prime, tangential, like that.
Would that be VB prime?
Yes, that's right. Remember, this angle here is equal to 20 degrees. All right, so remembering from our process, right? Tangential components remain the same. Right, so that means is that VA prime T, the tangential component for A, is going to equal whatever your tangential component for this one is, right? And this one, we know that it's going to be VA, right? So if you take the component out like that and like that, right? The tangential component is going to be negative. So that's going to be VA. Where's Mr. Machella? Mr. Machella, are you there? Can you tell me what this tangential component is going to be now? Is it cosine 20 or sine 20? Ah, he stepped out. All right. You guys know this. What's it going to be? Does anyone else know this? Sine 20, cosine 20?
Sine 20.
Sine 20. All right. So we have, and it's in the negative direction, right? It's in the negative tangential direction. So it'll be minus times VA in the, why does it say positive on here? Anyways, whatever. So this is going to be minus, it's in the negative direction, times 3 sine 20 meters per second, right? So that comes out to be equal to, all right, I'm assuming these solutions, the signs, they got them wrong. So apologies for that. So minus 1.0261 meters per second. All right, similarly, for VB prime tangential, it's going to equal VB tangential before impact. Again, this one is going to be negative, right? And remember that this angle here is equal to 20 degrees, right? So this is going to be minus 3 cosine 20 degrees. That ends up being equal to minus 2.8191 meters per second. And then you are conserving linear momentum along the normal direction, right? So conserve, so this is your t direction. Conserve linear momentum in your n direction. Right, so before impact, you'll have the positive component of VA in the positive n direction, right? So that's going to be cosine 20. So you get mVA cosine 20, right? And here for VB, it's going to be sine 20, but it's in the negative direction, right? This is where your signs are coming into the picture. That's why I was hesitant to write the expression out. You have minus m times VB, m times VB times sine 20, like that, right? And this is equal to m times whatever your normal components of your velocity are. So VA prime n plus m times VB prime n. All right, so this gives you one expression for these two unknowns. All right, so let's call this expression 1. The mass goes away. VA and VB are known, right? They're 3 meters per second squared. And the final equation you get from the coefficient of restitution. Right there, we know that the coefficient of restitution is equal to VB, the normal direction, VB prime minus VA prime in the normal direction divided by VA prime, the tangential direction, minus VB prime in the tangential direction, like that. All right, so what that gives us is that VB prime n minus VA prime n is equal to E times, oh, this is not tangential, this is normal. Ah, come on. All right. VAN times VBN. This is equal to E times VAN minus VBN, like that. All right. So writing that out, I end up with VB prime n minus VA prime n is equal to E times VA n minus VB n, right? And this is equal to 0.9 times my velocity in the normal direction. For A is VA cosine 20. So you have VA cosine 20, and you'll have minus, but remember, the sign you have to be careful. So there's going to be a minus minus in here for VB prime, right? For VB, because you have to account for the sign change. The relative velocity doesn't care if you're positive or negative. It needs to know what the overall negative velocity is. So you have to account for the fact that VB is going to be in the negative direction. So it's similar to here, minus VB sine 20. So you have minus VB sine 20. Right? And this gives you your second expression. And that's it, problem solved. I mean, you have to solve it, but that's the problem. And you already know what your tangential, and if you report it, in these perpendicular directions as vectors, that's totally okay. Or you could define a horizontal line, figure out what the magnitude and direction is after you know what these components are. Either way is totally okay. Leave it as a vector. All right, so know all 4 components. After. Good. All right, many thanks, guys. Homework has been posted. I saw there's a bunch of you who haven't submitted last homework as well. Please get that in soon. But other than that, thanks, guys. I'll see you all on Tuesday.
Thank you.
See you Tuesday.